This video builds on the last video, Introduction to Calculus. If you have not yet watched that video, you may want to consider doing so first. As we saw in the last video, calculus is about the concept of infinitely small change in one quantity compared to another quantity. For example, temperature with time. Let's look at how we can use this concept to help us find the area under a curve. Consider this curve, and we'll label the vertical axis y and the horizontal axis x. An example of where this is used is if the y-axis is speed and the x-axis is time. Then the area under the curve is distance travelled. Using this, we can tell how far a car has travelled, knowing only its speed over time. To find the area, we could start by making a series of rectangles under a curve, then add the area from all these rectangles, and that would give us an approximation of the total area. From the last video, we saw that we often use the Greek capital letter delta to represent change. So we can express the width of these rectangles as the change in x, delta x. The height of each rectangle is the value of y at that point, so each rectangle has an area of y times delta x. The area of all rectangles together is therefore the sum of these rectangles. The Greek letter sigma is usually used to mean sum, so the total area is the sum of y times delta x. But we can see that we are missing out on all this area. How can we cover more? If we were to make delta x smaller, our rectangles get narrower, meaning we cover more of the area under the curve. Then our area gets more accurate. To get the exact area, what we do is make the rectangles smaller and smaller. And in doing so, you can see that the area gets closer and closer to the real area under the curve. In fact, if we make the rectangles infinitely narrow, the area of the rectangles is the area under the curve. Just like in the Introduction to Calculus video, the delta x is getting infinitely small. To represent an infinitely small step in x, we use dx. But as the rectangles become infinitely thin, there also becomes infinitely many of them. So we replace the sigma with a new symbol called the integral symbol. This is to represent that it's an infinite sum. We call this the integral of y times dx. And it means the infinite sum of rectangles of height, y, and width, dx. This is an example of the core concept of integral calculus. Looking back, we can see that we broke down our complex shape into simple shapes that we knew the area of. We then imagined making those simple shapes infinitely small, narrow in this example, so that the area of all the simple shapes is the same as the complex shape. As you will find out, this process has many potential applications in engineering and science.